All right, welcome back. We're continuing with section 10.2 on Bronsted-Lowry acid-base theory. So in the early 1900s, 1923, the Danish chemist Johannes Bronsted and the British chemist Thomas Lowry independently and almost at the exact same time proposed a broadened theory for acids and bases. Previously, the Arrhenius theory had been applied, but the Arrhenius theory didn't really cover everything that scientists knew at that time qualified as an acid or a base. It was kind of a restrictive. And so the Bronsted-Lowry theory filled in those gaps that were present in the Arrhenius acid-base theory. So Bronsted-Lowry theory explained how non-aqueous acid and base solutions work. If you remember from Arrhenius theory, one of the key things is that Arrhenius theory is based on acids making protons or bases making hydroxide ions in water. And so Arrhenius theory only held true for solutions where water was the solvent. But we can have acids and bases in solutions where water isn't the solvent. And so Bronsted-Lowry theory explains what goes on with acids and bases in solutions where water isn't the solvent. Arrhenius acid-base theory also was restrictive in what counted as a base. In Arrhenius acid-base theory, only things that have hydroxide ions produced in water count as a base. But it was known that other substances that don't contain hydroxide also act like bases. For example, ammonia, NH3, there's no hydroxide there, so how is it able to act like a base in solution? And so Bronsted-Lowry acid-base theory was able to account for these other types of acids and bases that Arrhenius acid-base theory couldn't account for. So some new definitions of an acid and a base, according to Bronsted-Lowry. So an acid is a substance that can donate a proton to some other substance. So anything that can donate a proton to another substance is called a Bronsted-Lowry acid. So we call these proton donors or H+ donors. A Bronsted-Lowry base is a substance that can accept a proton, an H+ ion, from another substance. And so for something to be a Bronsted-Lowry base, it has to have a non-bonding lone pair of electrons. We'll underline that. So we oftentimes write Bronsted bases as a B, meaning like any base substance, and then we draw the dots to show it has to have a lone pair of electrons. The reason that Bronsted-Lowry bases have to have a lone pair of electrons is because when the base accepts the proton, protons don't have any electrons orbiting them, right? Hydrogen, the element, just has one electron. And when it gives up that one electron to become H+, the ion, it doesn't have any left. So to bond with H+, to accept a proton and make a new bond with it, the base has to provide both of the electrons for that bond. So we typically write the base as a B with 2 electrons next to it to show it's any substance that's going to be accepting that proton. And we know that that substance is going to have a lone pair of electrons able to make a new bond. And then for the acids, we usually write just HA to mean kind of any old acid in the general sense, with the H to show that that's what's going to be donated in solution. So HA turns into H+ plus A-. And this is the proton that's donated that originated from the acid. So again, some general equations for Bronsted-Lowry acid-base reactions. An acid is a substance that donates a proton. So for kind of any old acid, if we're just writing a general equation, we write HA, and it has a hydrogen that it's able to donate. And then the A represents the rest of the acid structure, typically the anion part, which is why we name it A, or use the letter A. And then the base, any old base, usually a capital B with 2 dots to represent that it's a Bronsted-Lowry base, which means it can accept a proton. And in order to accept that proton, it needs both electrons to make that new bond, because the proton it's accepting doesn't have any electrons to contribute to the bond. So when these react, the acid donates the proton to the base. And so you end up forming a new product, B with the H bound to it. And this is now an ion with the +1 charge. If it accepted one proton, the base was neutral. It accepted something with a positive charge. So now the new compound has a positive charge. And what's left over after the proton is donated is A minus with a negative charge because it lost a positively charged proton. And so that's the other product over here, A minus. So Bronsted-Lowry acid-base reactions, this acid donating a proton to a base that's accepting the proton, are in equilibrium. And so we write them with the double-headed arrow to show that they're reversible reactions. And because they're reversible equilibrium reactions, we can apply Le Chatelier's principle to Bronsted-Lowry acid-base reactions, meaning by changing the conditions, we can push Bronsted-Lowry acid-base reactions to favor products, push it to the right, or we can push it to the left to favor reactants. So for example, if we decrease the concentration of the acid, remember from chapter 9, these square brackets means the concentration. So if we decrease the concentration of the acid, according to Le Chatelier's principle, we can predict what would happen to the other components of the system. So if we decrease, let me draw my arrow back here. If we decrease the concentration of the acid, then according to Le Chatelier's principle, equilibrium is going to shift to make up for that stress. And so if we decrease the concentration of acid, the reaction is going to try to make up for the loss of acid. So it's going to push the equilibrium to the left because it's going to try to make up for this acid that we removed from the system. So it's going to favor the reverse reaction. So that means the concentrations of our products, the base after it's accepted the proton, and A minus, the acid anion, those concentrations are going to decrease. These are going to go down, because the reverse reaction is now favored. So these are going to be used up because the reverse reaction rate has been temporarily favored. We're going to produce more of the original base, and the concentration of HA, so that goes up, is going to return back to where it was until equilibrium is again restored. And so this is why we spent so much time in chapter 9 talking about equilibrium and Le Chatelier's principle, because it applies to acid-base theory. And it's something we're going to continue to talk about, pushing acid-base reactions to the left or to the right as we go through chapter 10. So Bronsted-Lowry acid-base reactions involve what are called coordinate covalent bonds. And this is a bonding pattern we talked about all the way back in chapter 5, but it just means that when you form a new bond, instead of each atom involved in the bond contributing one electron to make the bond, which has 2 electrons in it, one of the atoms contributes both electrons. So this case, water H2O is acting as the base because the oxygen on water has 2 lone pairs of electrons. And so hydrogen ion H plus can form a bond with one of those lone pairs to make this new bond right here, and to produce what's called the hydronium ion H3O plus. And again, coordinate covalent bond, it just means that both of the electrons in the bond came from one atom instead of each atom contributing 1 electron. And Bronsted bases have to have a lone pair of electrons because protons don't have any electrons to contribute to the bond. So when you form a hydronium ion or the product of a Bronsted base with a proton, it's going to be due to a coordinate covalent bond. So Bronsted-Lowry acids and bases also work in pairs. For a Bronsted-Lowry acid-base reaction to happen, you always have to have the proton donor, the acid, and then there has to be something that's going to accept the proton that the acid donated, the base. So they always work in pairs, like an acid and a base reacting together. And so you're always going to have an acid-base pair on the reactant side And then you also end up with an acid-base pair on the product side, because once your acid reactant, your H plus donor, donates a proton to the base, which is an H plus acceptor, according to Bronsted-Lowry acid-base theory, the products that you form, since this is an equilibrium reaction, could also act like acids and bases and go back to the reactants. So when HCl, the acid that's on the reactant side, donates a proton to water, you make H3O plus. Water gains a proton. And then you end up with Cl minus as your other product. But this reaction is reversible. And so H3O plus on this side could donate a proton back to Cl minus. So H3O plus hydronium ion on the reactants, on the product side, could act again like an acid to donate a proton back to chloride ion, which could act like a base. And so they always work in these pairs. You have an acid and a base on the reactant side that starts the reaction. And then you make an acid and a base on the product side. And that could go in reverse because the acid that you make on the product side could donate its proton to the base and the whole reaction could go backwards. And so the new acid that's made could be a proton donor. And then you have a new base that's also made that could accept a proton. So these reactions, again, they're reversible. They can go back and forth because you start with an acid and a base on the reactant side. And then the acid and the base that you make on the product side could go through another acid-base reaction to reform the reactants. So we have terminology for these new acids and new bases that are made with Bronsted-Lowry acid-base reactions. So the acid reactant is going to make what's called a conjugate base product. So when HCl donates its proton, right, the H plus goes to water to make H3O, what's left is Cl minus. And so the original acid makes a new base, a new H plus acceptor, and we call that the conjugate base. The original acid, reactant acid, makes a conjugate base. It loses a proton to make a base. And so the conjugate base of an acid only differs by the removal of one proton. So let me get rid of some of this extra stuff. So when HCl, our original acid, loses one proton, here to here, minus one H plus, it makes the conjugate base of that acid. So we'd say that the acid in this reaction is hydrochloric acid, HCl, and the conjugate base of that acid is Cl minus. They only differ by the removal of one proton. Water does the same thing. So water starts out as our base. It's going to accept a proton from HCl, and it forms H3O plus. So the original base reactant is going to make what we call the conjugate acid. On the product side of the equation, the base, which was originally a base on the reactant side, because it accepted a proton, it now acts as what we call the conjugate acid. So this only differs by plus one proton. So you can identify conjugate acids and bases by looking for what only changed by the addition or removal of one proton. So HCl to Cl minus, minus one proton. So that means that HCl donated a proton, it lost one, resulting in the formation of a base, and we call that new base the conjugate base. And from water to H3O plus, there was a gain of one proton. H2O to H3O, an additional H was added. So when you add an H, you make an acid. And so this is called the conjugate acid of water. So again, conjugate acids and bases, they're only going to differ by the loss or gain of one proton. So we call the acid and the base in the reaction the original acids and bases that are on the reactant side. And then on the product side, the base that's made from the original acid when it gives up a proton, we call that the conjugate base. And a new acid that's made when the original base accepts a proton, we call that the conjugate acid. So there's always these pairs working together in Bronsted-Lowry acid-base reactions. You have an acid and a base on the reactant side, and you have an acid and a base on the product side. And then you can track the acid from the reactant side made the base on the product side. And the base on the reactant side made the acid on the product side. And the ones on the product side we call conjugate because it was derived from the one on the reactant side. Okay, so let's kind of practice conjugate acid-base pairs. It's a really important concept, and you'll definitely be getting some quiz and exam questions asking you to identify the acid and the base, and then the conjugate acid and the conjugate base in a chemical reaction, an acid-base reaction. So let's do that. Let's label the acid and the base on the reactant side, and then let's label the conjugate acid and the conjugate base on the product side. Okay, so acids donate protons and bases accept them. So we have HF, which is hydrofluoric acid, and water, H2O, liquid. And if we check HF, if you didn't immediately know which one was the acid and which one was the base, you can try to figure out which one gained a proton and which one lost a proton. So HF goes from HF to F minus, so lost or donated 1 H plus. So if HF donated a proton, after losing the proton, you just have F minus left. That means that HF is the acid. Let me color code that so it stands out. And again, that's because it donated a proton. Now, if we check what happened to water, water went from H2O to H3O plus. So water accepted 1 H plus. It accepted or gained 1 proton. So a Bronsted base is something that can accept a proton. So this is the base. Now, if we want to figure out the conjugate acid and the conjugate base, on the product side, whatever can donate a proton is the conjugate acid, and it was derived from the original base. So our original base was water. It gained a proton to make H3O plus. So H3O plus is our conjugate acid. H3O plus now kind of has this extra proton that it could donate back to F minus to do the reverse reaction. So our conjugate acid is H3O plus. It's the new acid that was formed when the base gained a proton, which means that our conjugate base is F minus. So you should be able to dissect a Bronsted-Lowry acid-base reaction like this and identify on the reactant side the acid and the base, and then on the product side the conjugate acid and the conjugate base. And you can figure it out by looking at what gained, what accepted versus what donated a proton. So HF donated 1 H plus, HF turned into F minus. So F minus doesn't have the proton anymore. It means it was donated. So we can identify HF as the acid. And whatever is missing 1 proton on the product side, that's going to be your conjugate base. And then H2O went to H3O plus, so it accepted or gained 1 proton. So that means water was the base. It accepted the proton. That means it's a Bronsted-Lowry base. And H3O plus is therefore the conjugate acid. It differs from the base by the addition of 1 proton. Okay, so let's do some more practice with writing formulas for conjugate acid-base pairs. That was kind of dissecting a reaction to identify all the parts. So let's figure out the formula for the conjugate base of HSO4 minus. So conjugate base means that we want the base of this acid. So if this was acting as an acid, it would donate a proton. So the conjugate base is going to be this acid after it's donated the proton with one proton left. So SO4 2 minus. The conjugate base of phosphoric acid, H3PO4, is going to be the base that's formed after phosphoric acid donates one proton. So that would be H2PO4 1 minus. When it donates a proton, it loses a positive charge. So the new conjugate base, its charge decreases by 1. Okay, conjugate acids. So we want the conjugate acid of nitrate. The conjugate acid means if nitrate acted like the base and gained a proton, what would be the new formula? And so if you add a proton to nitrate, it acts like a base to make a conjugate acid, you get HNO3. Okay, HC2O4. So if this gained a proton, conjugate acids and bases differ from their original acids and bases by the gain or loss of one proton. So we're finding the conjugate acid of this compound. And when you're finding the conjugate acid, it's gained a proton. We want to make something that's acidic. So that would be H2C2O4. And when you gain a proton, you gain a positive charge, which means that this -1 charge ends up being, when you gain a +1 charge in the proton, the overall compound ends up being neutral. So key things to remember: conjugate acids and bases. Acids and bases only differ by the addition or removal of one proton. So a conjugate acid, because you're making an acid, it's going to have one additional proton compared to the base that it originated from. So here in C and D, we were finding conjugate acids. So we took the base and we added one proton. In conjugate bases, like in A and B, you're making a base by removing a proton. And so we're going to take our original acid, in this case HSO4, and remove one proton. Or in the case of phosphoric acid, remove one proton. And when you remove a proton, you're removing a positive charge, so you need to adjust the ion charge appropriately. And on the slides online, I gave you the answer so you can kind of check your work there. Okay, so we're next going to talk in section 10.3 about some more acid-base terminology. I'll see you then. Thank you.